Good afternoon. And it was a matter, as I indicated, when the people there at the Principal Solar Institute asked me to conduct this webinar. I looked at it and said, it isn't a matter of what do I put in, it's a matter of what do we leave out. There's a great deal of material to be covered here. I have selected a few items. We could have easily made this a week-long session. That said, as Rick indicated, you're welcome to type questions. We'll handle the bulk of them at the end. But I'd like to recap just a couple of points here. Number one, this is me. I run a consulting firm called North Texas Renewable Energy Engineering. My email, and you are welcome to contact me after the session at any time with follow-up questions and so forth. To recap just briefly, as Rick indicated, I am a voting member. There are 68 people on the UL 1741 and IEEE 1541 standards technical panel. This is the group of people that author the UL 1741 standards for the United States, and ultimately it serves as a template for safety for most of North America and, in fact, for much of the world. And, in fact, if you were to take a look at the Chinese safety organization known as CCC, their safety standard in China is patterned remarkably after 1741 here in the United States. I'm also a member of the Solar America Board for Codes and Standards. It is a large group of volunteers, particularly from a number of industries, where we take input from everybody. It gets condensed down. Larry Sherwood, the organizer for Solar ABCs, does a phenomenally good job, as do other people in the group. And they take input and condense it down, and it gets funneled toward both the work group within our own organization and within our industry for the National Fire Protection Association, better known as the National Electric Code, or NFPA 70. I am also part of the Electric Power Research Institute Smart Grid Development Committee. We're running on a power grid that was designed more than 100 years ago, and it shows. So, that said, let's proceed into just a little bit. I don't know the range of technology of the participants here today. I hope that we're not going to overwhelm the people that are not terribly technical, and at the same time, take a look at the items that will not bore other people here that are more advanced. I'm going to be talking today a little bit about microinverters, AC modules, DC optimizers, string inverters, and central inverters, how they're the same and how they differ. More importantly, there are a lot of facts and fiction that tend to float around in our industry with regard to what is and what isn't. We're going to take a look at where they overlap and where they are more distinctly utilized more advantageously. Also going to take a look in the crystal ball, a little bit more into the future, and see how that plays into things. Just the basics for those people that maybe are a little less technical. The numbers here are my own, but allow me to utilize my more than 40 years experience in the industry to arbitrarily assign some of the values. Microinverters are typically a 400-watt maximum small inverter, and it is a standalone inverter. However, they are usually attached to the photovoltaic module frame or mounting rack. They can, if you wanted to be silly enough, mount them 100 feet away, and as long as you run code-compliant wiring and everything else, there's nothing to prevent you from attaching 10 or 20 of the microinverters on the wall, let's say in your garage or elsewhere. Do they do it? No. It's a matter of economics and common sense. Microinverters all have grid-ready AC output. AC modules are, in fact, a microinverter, but they are PV embedded. The National Electric Code, Section 690.2 and .4 delineate specifically the definition of an AC module. It is a permanently attached microinverter. It is attached to the PV by the manufacturer. Whether that's done by the PV manufacturer or elsewhere, it does not matter. It is marketed as a complete unit with PV and inverter attached. Like the microinverter, it too has strictly AC output. Optimizers are another technology. They connect to PV similar to the method in which microinverters are attached to PV. they adjust the individual PV output current to match the current from the other PV in the array. Now, the voltage will go up and down from that optimizer, but the current will try to match those in all the other panels to which it's connected. It has DC output. There are two kinds of optimizers in use today. One just simply goes straight across, meaning if you feed it with, let's say, 30 to 40 volts DC input at 8 amps, it will strive to come out with approximately whatever current is present in the remainder of the array and adjust its output voltage to match that current. I know this is a little bit technical, but it becomes more of what's called a constant current device. There's another concept also in optimizers where they're actually stepping up the voltage from the PV level to some high voltage, say 300 to 400 volts, which reduces the current and subsequently reduces the size of the wire required and consequently the losses involved. It again is DC output only. Now we get to what we most are familiar with, and that are the string inverters. You connect 10, say 12 solar modules or photovoltaic modules in a string, one to the next, just like flashlight batteries in a flashlight, head to tail, hence the name string. They tend to run in the 2 kilowatt to 30 kilowatt range, and again are strictly AC output. Central inverters are large. Typically, they require a crane to move. These are utility scale by definition, typically 100 kilowatts up to 1.5 megawatts or million watts, and some are even getting larger now. They are AC output only, and virtually all are three-phase. You will not find any of those used in a residential or even a commercial scale application. They tend to be too large. You will occasionally find very low end, and we'll call them 100 kilowatt, in a large industrial / commercial, but not often. They're just simply too large. They usually require a concrete pedestal just due to their weight. Those are the technologies that we're going to be discussing today. To start out, I'd like to differentiate, first of all, clearly between microinverters and AC modules. I know there's been a bit of blurring in the definition. A lot of the marketing people in our industry today have taken a lot of artistic license with this. Microinverters are standalone. As you note on your screen right now, the microinverter on the left has clearly got a couple of slots on it where screws would mount that to the photovoltaic module frame, racking, or elsewhere. It's got leads attached to it for the PV DC input. Those are the smaller leads, and the AC. In this particular case, that model of inverter has the alternating current passing from one to the next through the inverter. Others have an external cable that runs from one inverter to the next, and they have a snap-in or other connection. Where do we use these? Well, the nice thing is they allow for what's called an incrementally sized system. You can start out fairly readily with 2 or 3 or 4 or 5, whatever your budget and other constraints allow, and then at some future time add more. They also work well in areas that are unsuitable for string systems, where you cannot put all of the PV modules in an array contiguously where they all face the sun at the same angle. Let's say that you have a string inverter system that requires 10 photovoltaic modules, and then you have space for 14, and you'd like to maximize the use of your available space. Some people will have gone ahead and installed the 10 with a string inverter and call it good. Other people can go back and say, I can fill in the remaining space of 4 with a microinverter or an AC module. Another thing is that the marketing folks have done a very, very good job of selling these, and customers say, that's what I want. You sell them what they want. AC modules, if you'll note in the image on the right, those are actually attached already to the backing of the PV module. They are attached, whether it's by the photovoltaic module manufacturer or the inverter manufacturer, but they are sold as a complete product. There's generally less labor involved, only because they don't have to be attached in the field. And also, unlike microinverters, you know that the PV module to which it's attached already is perfectly matched for that particular model of AC module, in this case the microinverter attached. So why use them? You may find that you have installations that work in perfectly good, clear sunlight, and you say, well, okay, here might have been an application. I don't know that this would have been a perfect justification for it. But shade happens. Trees grow, and sometimes they grow taller than you're told they're going to grow. Ask me how I know. In our case, the trees were supposed to stop growing at 30 feet, and they're now 40 feet and still growing. So we have a little bit of a shade issue at our home, only in the winter. Here you got ducks sitting on PV. They're shading the PV. Would I recommend installing an AC module or microinverter or optimizer in that case? Probably not, but shade happens. And when you have something like this, it may be temporary, and yet it's still going to impact the production in that particular system. But there are also other causes that shade creates issues that are difficult to quantify. Ideally, you don't want to install a system where you're going to have shade issues in the first place. String inverters. These require typically multiple 8, 10, 12, sometimes 14 or more series-connected photovoltaic modules. You'll feed them with anything from just 200 or 300 volts up to 1,000 volts. And they convert that higher voltage DC into, depending on what they're connected to, 120 volt, 208 volt three-phase, 240 volt, what we call biphase or split phase for a home, and so forth. The one inverter on the left is attached to a home. That's a 240 volt, and the photovoltaics will be on the roof or located elsewhere. Very clean, simple installation. Common question, can they be connected to each other, multiples? Clearly the answer is yes, as exemplified on the right. Yes, inverters can be connected in parallel. In fact, in large arrays, they always are. Central inverters tend to be very large, generally ugly looking, just boxes. They're very plain, very unassuming, almost boring in appearance. Yet it's doing some electrical magic, converting the direct current from the photovoltaic modules into grid-ready alternating current connected to the utility grid. The system on the left is a smaller, particular, in this case, central inverter. The array on the right belongs to Tucson Electric Power. Each one of the white, almost invisible little squares that you can now see on your screen are, in fact, a central inverter, and there's one for each group of arrays that you see there. So they've run all that wiring from each square of PV to one inverter, and then all the inverters have wiring run underground to a common point where they're then connected to the utility grid. In this case, this is a I believe it's a 4.6 megawatt system in northeastern Arizona near the town of Springerville. Now we get into the meat of the discussion today. Myths, legends, and facts. Some of what you hear, and to no one's surprise, is myth. It's hype. But they're doing a marvelous job of it. Gee, it's sort of like the less filling, great taste, Ford, Chevy, pick your argument here. It also depends on who you ask. I recall a children's story where a small bird was walking down a path and was struck on the head by an acorn, and because of that, the sky was falling. And soon, that little chicken had everyone believing that the sky was falling. Why? Because a piece of it hit him on the head. Number one, probably first and foremost in our industry, is the discussion about what are called electrolytic capacitors. Electrolytic capacitors are thought to be the most evil thing if you listen to some people, and yet you look at some of the more notable companies in our industry and they're using them in large quantity. So what are the facts? Some manufacturers say, hey, they're perfectly fine. Some people say they're not. You're better off using a different technology known as a film capacitor. Before we get into this, one of the things that I need to explain is what is meant by failed and worn out. If you go out and buy a set of tires for your automobile, and next month the tread on one separates, that's failed. You can't drive it, you take it back, you get a new one, you put it on the vehicle. You take that same set of tires, everything works perfectly, you drive 80,000 miles, now you're down to virtually no tread, and they say, okay, now they're worn out. Can parts fail? All parts can and do fail, whether they are what we call electrolytic capacitors or film. Electrolytic capacitors internally resemble a roll of paper towel almost. It's almost like you took a layer of the paper and you wrapped aluminum foil, put it on both sides, and then wrapped it in a big circle. It's got an oil type material on the inside, and that's the way it works. Well, what happens in an electrolytic capacitor? I'm going to go back quite a number of years ago. I don't know how old many of you are. A few of you might be old enough to remember tires. I remember tires in the 1960s that you could buy, and the premium tires that were available had 24,000, maybe 30,000 mile lifetime warranties on them. Not so today. As a matter of fact, the junk tires have more than 30,000 miles. We're talking tires today, 80,000, 90,000 mile tires. I know that this is a fact. Just put some tires here on the vehicle not long ago, had 88,000 miles on them. They were getting a little bit worn. On the other hand, if I took a set of those 80,000 mile tires and we put them on a fairly high-powered, let's say, Ford Mustang, and hand the keys to a son or a relative or a friend and say, here, I'll buy your tires, I'll buy your gas, I'll pay your insurance, have fun. You think those 80,000 mile tires are going to last 80,000? We all know the answer. The point is that you might be lucky to get 10,000 or maybe 15,000 miles out of those tires. If you abuse a part, you use it in a manner outside of its specifications, you can take the absolute most premium component and wear it out well ahead of its expected lifetime. So what happens in the case of an electrolytic capacitor? If it's not usable anymore, how do we define worn out? Well, there are internal losses within a capacitor, meaning it gets a little bit warm on its own when it's used. And a capacitor is worn out when one particular value, and it's called, if you want to make notes, it's called the effective series resistance, which we abbreviate ESR. And we say that when that is, a capacitor is worn out when it's double what it was at new. Failed, well, failed means it blew up. Excessive voltage or other problems, abuse will cause that. Now, let's take a look at it here. In a worst-case environment, how long will an electrolytic capacitor last? I could have done a thesis on this. In fact, I almost did. In extensive analysis using Phoenix, Arizona as the worst-case large metropolitan area, a quality electrolytic capacitor designed into the circuit properly and used within its ratings and specifications will last approximately 70 years before it's considered, and we say, worn out. And what's the impact on the inverter at that point? The inverter is a little bit less efficient. The waveform gets a little bit more distorted, but remarkably, it continues to run. Electrolytic capacitors are much smaller for a given value and also much lower cost. Here's an example. Now, let's say that the electrolytic capacitor example on the left was 22 microfarads at 400 volts. The image is not, but we're going to pretend that it is. It's film capacitor equivalent on the right. Look at the physical volume. The electrolytic capacitor on the left would occupy 4,400 cubic millimeters. If you can't relate to what that is, it's a quarter of a cubic inch. On the right is a film capacitor, 26,000. That's 1.5 cubic inches. A lot more volume for the same capacitance, but look at the cost. 36-inch in quantities of 5,000 versus $10.69 for the film. So why all the big hoopla about film? Well, some of you may remember many, many years ago when videotaping was just coming into vogue. And we get into a situation where the Sony Corporation had actually come out with the superior technology known as Betamax. Betamax in this particular application had better video quality and clearly superior audio fidelity. So why did VHS win out? Because Panasonic and Toshiba, Sony rivals, did a better job of marketing. And they convinced consumers that the VHS was the better way to go. Was it dramatically inferior? No, but it was inferior. Here we've got two technologies that if you do it properly on the left with the electrolytic, it will in fact last 70 years, and that's in Phoenix. You go to a colder climate, it lasts even longer. Keys here are you have to start out with a quality part. That's difficult to do when all of the push is for cheaper and cheaper product. Then you have to design it into the circuit properly. You really have to know what you're doing. A film capacitor costs a lot more. It's larger for a physical volume for the same equivalent value of capacitance. What do? They store electricity inside. They release it when needed. But then it allows the designer to be a little bit sloppier in some respects. Okay, so will it wear out? I think my favorite story is, hey, I know some wheels I can put on your car right now, and I guarantee you they will get more than 5 million miles before you even have to worry about them. Now, grant you, the ride won't be the greatest. A, B, it's not probably be very good for your mileage. But if you were to go out and take wheels off of a train car and put them on your automobile or something equivalent, you're not going to wear them out. But that's kind of what we're looking at here. Film works. They both are fine in the applications. It's just that people have convinced the mass populace that are out there shopping, and many of you that are not design technicians, that film is a superior technology. In a few ways it is, but is it really necessary? The answer is no, it's overkill. But we're being convinced otherwise. Some more myths and legends. Microinverters and AC modules are more efficient than string inverters. True, yes or no? Well, in fact, in systems without shade, and with all the PV parallel to each other facing the same direction and the same angle, the performance difference across the different kinds of products will be limited to the worst case tolerance variation in the photovoltaic modules. Now, someone might argue, hey, they could be plus or minus, and depending on the PV that you use, 5% typically today. Some of the manufacturers are coming out with minus 0 plus 5. They're getting the tolerances down just a little bit. This is where a cost-benefit analysis has to come into the picture. You're going to pay more whether you use optimizers or whether you go in with AC modules and microinverters. Is the increased energy output worth the difference in the product cost and installation? Microinverters and AC modules tend to be a little bit less intensive on the installation side, but they're also more support intensive should one or two fail. Here again, another argument. Gee, if one or two of them happen to fail, you've still got all the rest of them working, whereas if, say, a central inverter should fail, or even on a large residential system, let's say that the string inverter should fail, the system is completely down. Both are true. You need to look at it and say, where is the greater risk? None of them really have a clear-cut, gee, this is the best for all applications. To me, I look at it in terms of physical system size, orientation, growth, and a number of other factors. There is no one perfect solution for every application. When you look at a residence, let's say you don't have space for all the PV to be mounted contiguously in one array. You want one complete large south-facing, well, some direction. They all need to be facing the same direction. If there is a marked difference between a pair of panels or several, now you're not going to get optimal output even connected to a string inverter. That's where AC modules or microinverters may come in. That's not necessarily the better place even for optimizers. What optimizers do is take those minor differences among the panels and levels it out just a little bit. More importantly, if you do get a few panels that are shaded, happens. Sometimes it's absolutely unavoidable. They're willing to live with that reduced power for a period of time during the day. Optimizers there with a string inverter are a better solution. Where's the breakover point? And again, this is kind of a gray area to me. As I look at it, to me, systems that are one PV module up through about 5 to 10 kilowatts can very comfortably be addressed by microinverters and AC modules. They can also be handled by some of the lower end, size-wise, lower end string inverters. And if you do have shade issues, you might put optimizers on only those panels where the shade is going to impact the PV production. You will actually find that in some installations that are not experiencing any shade at all, optimizers can actually cost you a little bit of power. Not a lot, but they are not 100% efficient. Maybe 97, 98%. But often that's enough to actually, in a perfect, otherwise perfect system, reduce your output. Optimizers need to be used where you're going to have shading issues and where it's absolutely unavoidable. To me, the better solution is don't put PV where it's going to get shaded in the first place, but sometimes that's the only compromise available. Systems that experience unavoidable shading may see, in fact, up to about 30% increased output depending on the severity of the shade. And again, to reiterate, when you install them, you try to avoid shade in the first place. It's that simple. A few other points. Optimizers with string inverters are more efficient than microinverters. And to be candid, it's a toss-up. The advantage to the microinverters, they all come out with grid-ready AC. Microinverters, whether they're AC modules already embedded into the photovoltaics or a microinverter that gets attached to the PV. And I want to make sure that you understand that distinction. There are companies out there that have attached microinverters to the PV, and they are being marketed as an AC module. If you look at NEC Section 690, by definition, all of DC wiring is considered enclosed, not visible. And clearly that is not the case in all situations here. In that earlier image that you saw, there were microinverters mounted to the back of the PV in place of the junction box, zero DC wiring. There was only one cable that came out, and that's with the AC output. That is a clear distinction. Unfortunately, that is getting very, very much lost in the marketing hype, and kind of like the electrolytic versus film argument, probably one that those of us in the know are going to ultimately end up losing because the marketing people are doing a better job. Microinverter systems are more efficient than string systems. Well, let's look at it for just a moment. Is that true? The answer is not necessarily. When you have a string system, and this applies to questions number 3 and 4 here. When you have a string system, you have DC wiring that gets connected in series. You have the wiring loss itself. You have loss in each of the connector pairs. You have loss in the wiring coming downhill from the PV to then what we call balance of system hardware, BOS. That's a high voltage disconnect, something to open and remove the DC from the inverter. You have other protective devices that are now being required. All of those introduce small but finite losses in the system. In the case of microinverters and AC modules, that hardware goes away. You do have AC run directly up to the front, all the way down to the panel board where the circuit breakers are located. So, are they more efficient? Questionably. In certain applications, the answer will be yes. But let me give you an example. If you have a small vehicle, let's say that you go out and buy a Honda Accord, is that the most efficient vehicle for pulling, let's say, a 40-foot Airstream trailer? I would say not. Odds are, first of all, even if you could pull it, your mileage is not going to be very good. This is an application where a Chevy Suburban or a Ford F-250 would be the better vehicle. So they're application specific. And in all things, when you've got good sunlight, minimal shade, the differences appear on paper. It would take lab-grade equipment to measure the difference. We hear anecdotal claims, hey, I'm getting 25% more energy. Under what conditions? I could sit down and for every one of those anecdotal claims, show you another claim on the other side that says, hey, mine is more efficient. It's kind of the old less filling, great taste argument. Microinverters have a 25-year warranty. That means they're more reliable than string inverters. More reliable, I don't know. Here again, it all depends on how well they're manufactured, how consistently, the quality of the components, and so forth. We haven't gotten to the point where any of these companies are 25 years old yet. Number one, we go back to the point where what's to define? If it fails, that's one thing. If it's worn out, it's another. The warranty is only as good as the company behind it. And size is not an indicator of strength. I think for many of you that have been in the industry for any period of time can relate to a company known as BP. They manufactured a lot of photovoltaic modules, but they're not anymore. Number 6, microinverters and or AC modules can completely replace string inverters and central inverters. Well, they can. But is that the wisest move? The answer is no. As an example, let's say that you have to ship 10,000 packages. Well, you could put a few into a small car and send all 10,000 packages across country. Probably take 1,000 vehicles to do it. Or you could put them into a few trucks and ship them. Or you can put them in a train car and ship them that way, and it's all done. It depends on the size of the system. They want to make a one-size-fits-all, and there are systems right now that are out there that are using microinverters, and they are working, but are they the best application? I would question that. And here again, a cost-benefit analysis, my instincts say no. String inverters for medium-sized systems, central inverters for larger systems, AC modules and microinverters for all the other applications, for filling in, for the smaller systems, for any other things. And there are millions that are needed out there. There's room for everybody. Don't let the marketing folks convince you that one can do the job of all. I can show you examples where that is not the case. So what do we do about getting the cost down? Well, here's the problem. We get into a situation where people are clamoring for a cheaper product. And having been on the design side of this for more than a decade, I can appreciate that. We have all of this extreme downward pressure to get the prices reduced on the inverters and other balance of system products, and yet they're expected now to operate, as you've already noted, 25-year warranties. Installers say, gee, I've had a failure in this microinverter. The microinverter company says, fine, you roll a truck, I'll pay you $150 to go out and replace it. The microinverter company can't afford that, not for long, because that is far more than they made on the product in the first place. In fact, that's more than the product sold for today. We've also got some changes in the 2014 National Electric Code. For example, we're being mandated or told by municipalities that we have to have disconnects between every single photovoltaic module. It's a requirement for which right now no open common solutions exist, but they'll catch up. Problem is it's going to add cost back in. So while we've got this push to make them cheaper, we've also got the stretch coming up saying we also want improved quality and longer life. And something's got to give. Here's a possible consideration. When we look at the decreased cost on these products, one of the things that we have to look at is what percentage is that product of the overall system. As you look at this graphic, which was gratefully donated to me by our friends at the Rocky Mountain Institute in Colorado, this was data from 2012. And if you look, the average inverter cost is less than 6% of the total system. And we broke out the soft costs. The soft costs are a substantial portion of the total. 25%. Where can we work that will actually have a greater impact? If we reduce the cost of the inverters, microinverters, AC modules, and optimizers, if they were reduced by another 50%, you would find that that would only reduce the total system cost by maybe another 3%. There's not a lot more room to give in the microinverters, but there are some things that can be done. Number one, at least for the AC modules and microinverters, there needs to be a collaborative effort, particularly with the film PV manufacturing firms, to produce high voltage photovoltaic modules, 250 volts or higher. Now, this is difficult to do with a crystalline panel only because that means a lot more cells, a lot more connections. In the case of a film panel, it's a matter of changing the laser etch pattern. Yes, there are still some sacrifices, but here the greater good comes from raising the voltage on the photovoltaic module. Why? This eliminates completely the DC high voltage, if you will, circuit inside the inverters. That's half of the cost of the inverter right there. That's half the parts, and those are the more expensive parts. Those are what we call inductors or transformers, higher voltage, other parts. I mean, it literally reduces the size and the cost of that inverter by more than half. In fact, studies that we conducted showed that there was so little heat being generated if they could be fed with a 250 volt photovoltaic module that we could get away with thermoplastic. We could eliminate the metal altogether and even further reduce the cost of the inverter product at that point. You'd suddenly be looking at a component value somewhere in the range of 23 to 25 cents a watt. That is a substantial reduction, but remember, that still is only less than 6% of the total system, but it's still a huge step in the right direction. The advantages are it's running a lot cooler, it's smaller. Now a product of that size could easily be housed inside the junction box. Now you've eliminated the junction box and other things. I'm getting ahead of myself here just a little bit. You can make the hardware as what we call NEC code-friendly and installer-friendly as possible. This is a little difficult to do in certain cases because you've got more than 18,000 jurisdictions around the country, and everyone interprets the National Electric Code as they see fit. So what you provide to them are documents that make it as easy to get permits as possible, decrease the permitting costs. Now you're cutting into what we call the soft costs. Soft costs of the system are the intangibles. The inspector has to come out. You roll a truck. They look at it and say, oh, that isn't the way I think it should be. You need to change that, or I will not green tag your product or your project and allow you to move forward. The less of that you need to run into, the better. Steps are already underway, and I'd like to bring to everybody's attention a program through the Department of Energy right now called the Sunshot Initiative. The Dallas-Fort Worth area is very fortunate to be at least one of the participating regions in this new project to help unify the codes, standards, and permitting and help get the cost of installation down. So manufacturers do what they can to make the balance of system hardware as code-friendly and installer-friendly as possible. That decreases the labor costs. Number three, you consider designs that eliminate the photovoltaic junction box, bypass diodes, and cables. That's another 7% of the PV hardware cost. That is substantial. They fight for fractions of a percent, and now you're handing them 7%. If there is a way to mount them onto the PV, well, then you get concerns about what happens with the heat. Well, if it's a high voltage photovoltaic module, now you're only generating 2 or 3% of that energy as heat. You say, well, the PV module gets hot. In tests that we conducted, properly installed, we actually found that the photovoltaic module itself was benefited by having the inverter attached to it because the inverter acted like a heat sink and drew heat away from the PV. So when all things are considered, the temperature of the inverter tends to be very reasonable. And again, go back to the used quality parts. So looking ahead, where are we going? Things that I stepped back and I looked at, what I see I call neighborhood solar gardens. Not everyone's home is suitable for photovoltaics. You may live in a very well-treed neighborhood, a very mature region where you've got too much shade on your home. Or maybe you don't want to put it on the front of a south side facing, facing home. There are many unused areas in our cities today where you could actually create what I call solar gardens. Build a photovoltaic array, allow people to buy 10 of those modules, and then be credited with the value of that energy production for those 10. They haven't affected their home. They haven't impacted anything around them. Active power factor correction. Power factor is a horribly misunderstood and often mismarketed term, but utilities do correct power factor by throwing in capacitor banks in various neighborhoods. This would be very important to be able to do this for a utility. In other words, it's a difficult thing for the utilities. Residential people, they don't care because they're not being charged for reactive power, but utilities are concerned by it, and if they had a way of adjusting constantly the active power factor, if you will, that would be a huge benefit. Energy storage. There's some marvelous revelations coming out in energy storage, much smaller batteries, much longer lived batteries, and so forth, where a utility might be able to command an inverter into a momentary surge output mode. I joke about it and call it grunt mode. Maybe for a short time you need excess energy being dumped to the grid while they get some rotating reserves brought online should a power plant go down. I see this happening. So we have energy storage not only for, in this case, peak demand, but for surge peak. And that's what I call intelligent load control. You work in a large industrial building, you get a couple 200 horsepower compressors they want to kick on at the same time. Those of you that have worked in the manufacturing or industrial sectors know that many of those industrial meters have got what they call a peak demand needle or some other indicator on them. And if you go way up even momentarily, so does your bill for the next several months. If we have a way of controlling the peak demand that's consumed and allow them to come on slower, maybe only one at a time, maybe command the inverters into a momentary grunt mode to decrease that peak, again, it benefits the customer substantially. So I see intelligent load control by energy producing devices, and all of these neighborhood solar gardens I see in the next 1 to 5 years. Active power correction probably in 5 years, storage 5 to 10, and intelligent load control 5 to 10. That's a rough time frame. Smarter use of the power we generate. Quick example, I do have an off-grid home, as Rick indicated. If I have excess energy on a given day, the batteries are full, I'm not using much, hey, let's use some of that extra to maybe pump some water into storage. Or maybe I could run an air conditioner that could be controlled by the loads. And in this particular example, I might be able to chill the freezer down a few extra degrees for no energy penalty, so that at night it's not using quite as much, or at other times. Improved energy storage, I touched on that a moment ago, but those are the batteries. We're seeing some incredible new technologies coming out. Hybrid on-grid, off-grid. SMA, for example, has got one right now where they will provide a minimal amount of power should the utility go down. They incorporate batteries into their system, but as these new battery technologies come into play, we're going to see that more and more commonly. Are they going to replace and completely take over the control and power a home? Probably not. That's still going to be too expensive. But if you have emergency lighting, if you have telephones, if you have other appliances that urgently require power in the event of a failure, an oxygen generator, those are excellent applications for on-grid, off-grid, hybrid. Everybody I know says, oh, I want to keep the food in my refrigerator cold. That's lower importance, but not to everybody. The intelligent load control, again, same thing. We're going to see less demand during the peak periods. The utility may be able to command certain things. That's been around for a long time. It's now becoming more predominant. Feed-in tariffs, meaning what do they give you for the energy that you're backfed? Here in Texas, we've got utilities, co-ops, for example, that will give you nothing at all. They're not regulated by our State Public Utilities Commission and so forth. As the feed-in tariff rate becomes more standardized, more stable, more people will become interested in it, particularly if it gets close to what they're now paying at retail value. There's an argument between retail and wholesale. That's a whole different political issue for which we didn't have time in today's discussion. Okay, that pretty well wraps up. I realize we've only had a very short time to just touch on a few key points here. We could have made an entire year-long discussion out of this. I am open to questions at this point. Rick, it's all yours.
Great, Dan. Thank you very much. That was a great overview of the inverter landscape. And again, I remind all the participants, please chat your questions. You can send them to all panelists, or if you want to share your question with the entire audience, then send a chat to all participants. The first question, Dan, came from Stephen. Can microinverters provide reactive power, which is becoming increasingly important?
Stephen, the answer is yes, if they are designed appropriately. I realize the term reactive power is probably foreign to many people. Let's try to keep it simple here for a moment. When we talk about electrical voltage and electrical current, while they're associated with each other, they're still, in fact, two different things. Electrical voltage would be like the pressure of water in your water pipe. The current, on the other hand, would be the amount of water being pushed. Now, if I were to measure the amount of water, for example, going into a swimming pool, I run my garden hose into that pool and I turn it on full blast, it may be several minutes of water running before I can actually detect more than just a very thin layer of water in the bottom of that pool. Whereas if I'm running that same water into a cup, in a matter of a second or two, that cup will be full. Well, the time lag between when the water starts to flow and when I can measure it, or in this case, when the voltage is applied and when we start to measure current flow, there may be a difference between the two. And we refer to the difference between the voltage and the current in time as power factor. It's a very, very difficult concept. Stephen, yes, with the newer technologies, as a matter of fact, even today's inverters with the proper programming could, in fact, generate what is called reactive power. It's just that under the earlier versions of UL 1741, we weren't allowed to. Now utilities are coming back and saying, but we want it. So yes, they can. That is the simple answer.
All right, great. Next question from Greg. Do you have any white papers on today's subjects? The references would be very useful to dispel the myths.
The answer is not yet, but I'll tell you what, that's an excellent question. The Principal Solar Institute executives have asked me to put together a white paper. I will do so after the webinar here. Bear in mind, I'm swamped at the moment. I will get it out as quickly as I can, and we'll hand it to them, and it will appear on their website and be available for download.
And Greg, just to let you know, if you subscribe to the email subscription list at principalsolarinstitute.org, we will be sending out that announcement when that white paper is ready. And the next question is from Bill. What happens if the panel watts exceeds the capacity of the microinverter? Does it shorten the life of the inverter?
Great question. Bill, I'm glad you asked. The answer is it might. Most of the microinverters today are designed to limit their total wattage output on the AC side. Think of it like a governor on an engine. At one time or another, maybe most of us have rented a large truck or driven a large rental truck. They had governors on them to limit them to 55 or 60 miles an hour, so that no matter how hard you pushed your foot to the floor, 60 was the top end. Well, in an AC module or microinverter, if you attach a photovoltaic panel, let's say to a microinverter that is much larger in wattage rating than the inverter is designed to output, the output circuitry today will limit its output to a safe value. Now, it's commonly mistakenly called clipping. I don't like that word because it implies distortion. I call it limiting. What it will do, however, is generally speaking, it will cause the microinverter to run a little hotter through the course of the day than it might otherwise. Pretend you have a 250-watt microinverter, and you attach it to a, we'll call it, quote, 250-watt photovoltaic module. Interestingly, the only time you'll get 250 watts from that photovoltaic module is on a very bright, cold winter day when it's about 0 degrees outside. And at that point, the inverter is going to be running fairly cold and very well within its normal range. On the other hand, let's say you hook it up to a 350 watt. It will not damage the inverter, but it will shorten its life by some fractional amount, quantity of which I cannot tell without further analysis. So you're better off connecting them to a panel of its prescribed rating or a little bit larger. How much larger? I would not exceed the inverter rating by more than 10%. So if you've got a 250 watt rated microinverter, 275 is acceptable for the photovoltaic module, but anything larger than that is starting to push it just a little bit. I hope that answers your question.
Great. And if there's another follow-up question, go ahead and post that. Dan, the next question, in a commercial installation of 100 kilowatts, how would you choose between string inverters and microinverters when you're kind of on that boundary edge?
This becomes a cost-benefit analysis for both the installation firm and how you're, generally when you have a larger system of that nature, are we consuming all of it on site, or is there what is called a power purchase agreement in place, PPA? Does that backfed power have value, and if so, how much? Typically, you'll see maybe 1 to 2% variation, all other things being equal. Completely clear, no shade, all of the panels perfectly organized on a commercial rooftop and so forth, 100 kilowatt system. The only difference is going to be across the panel tolerance variations, which tend to be 2 or 3%. You're going to find some of them a little higher, some of them a little lower. Many of the better panel manufacturers today are coming out with panels that are -0 plus 5%, for example. That means they're guaranteed under standard test conditions to produce their rated value or more. So when you design a system, you look at it and say, okay, which is of greater value to me? The value of the energy or the cost savings in the installation? There's not a cut and dried black and white answer to your question. It's a great question, but you have to analyze which is more beneficial to the customer. The slightly increased value of the power production or the decreased cost of the total system installation.
Okay, great. Next question. You seem to be very positive about the idea of a 250-volt photovoltaic panel for film PV. Are there any new safety issues or other disadvantages that you would experience with 250-volt PV?
Not really. Aside from the fact that, you know, I would not normally recommend that high a voltage for a string system. You'd have to parallel too many of the photovoltaic modules. I'm advocating the high voltage PV for the microinverters and AC modules, because in that case it would allow those manufacturers of the microinverters and AC modules to eliminate more than half of the components in their product. It shrinks the size, it decreases the heat, it lowers the cost. It's a win-win-win all the way around. It is not readily doable in a crystalline technology, but it is readily doable in the film technologies where they are laser etched. That determines the output voltage in that case. Again, to reiterate, I don't recommend high voltage PV in this application for the purposes of high voltage PV in an array. Now there is one, we'll call them an optimizer. I even hate to use optimizer because it's not really in that sense. There's a company that actually is producing a DC to DC converter that'll take the 30 to 40, 45 volts from a typical photovoltaic module, and it'll step it up to around 300 or 400 volts, and they'll all get hooked up then in parallel automatically to a common bus. And by raising the voltage, you can now use smaller wire just like you would in a string system, with the advantage in that particular application of should one photovoltaic module fail, whether it's damage to it from hail or some other source, the rest will continue to operate. But for the most part, again, no, I do not advocate high voltage photovoltaic modules for string systems, but I do for AC modules and microinverters.
The next question is it true that residential performance monitoring per module for PV monitoring helps homeowners?
To a point. What we have found over the years is that they're like all the gauges in your automobile. Car manufacturers for a long time handed us what we all kind of jokingly referred to and may still as idiot lights. All you care about is it working right or not. Then for a while, cars came out with lots of gauges. Well, one of the things that we have discovered is that when you have per panel monitoring, people who keep track of that and they look at it diligently oftentimes are overly and unnecessarily concerned when they see 212 watts from one inverter and only 203 watts from another. And they're quickly on the phone with their installer saying, hey, I got a 9-watt difference here. Is there a problem? I don't want to have a, can you get out here? I want to fix it. No, there are variations, even just the 2 or 3% variation in tolerance among the PV will show that. And unless you've got an extremely knowledgeable homeowner that knows not to get worried about that, oftentimes we're finding now that individual monitors on each one of them is creating more of a headache for the installers than it's solving. So having something that's more of a green, yellow, red light, high, green light, everything's within normal operating parameters. Yellow, hey, I got a duck out there sitting on one of my solar panels. Or red, it's not working at all. I would advocate more of that kind of an application. Without that, you're just driving the poor installers to insanity at this point. And then it loses its luster after a few months, and the homeowners tend not to pay much attention to it afterwards anyway. So I find that panel-by-panel monitoring is a nice toy for 1% of us and an annoyance for the other 99%.
And I'll take one more question. I've heard that microinverters have a mean time between failures as high as 300 years. Does this mean they are that much more reliable than string inverters?
The simple answer is no. Some of you may recall here marketing, I'd say within the last 2-3 years, that showed remarkably high numbers for what we call mean time between failure in any given product. Well, you can do all kinds of marvelous things with numbers. We're finding that the capacitors, of course, wore out long before that. And so, no, they are not necessarily more nor less reliable. They're about the same. The one thing that I would like to mention is that many of the string and larger central inverters, they incorporate huge electrolytic capacitors. And as long as they follow the same guidelines, if they go in with quality components and design the circuits intelligently, and that takes a good bit of work on the part of the engineers, those units, even in the hottest of climates, its heat is the #1 enemy of the capacitors, even in the hottest of climates, they will easily last 60 to 70 years.
Okay, excellent. Well, Dan, thank you very much for your presentation today. That's all the time we have for questions. I posted a link to Dan's profile on the principalsolarinstitute.org on our webpage. You can send a message to him there. We will also convert this recording into a YouTube video. We'll post the recording with the audio and visuals along with today's slides. That's the link that you see in the chat, and we will also send an email to everyone whether you attended or not. You'll receive that email tomorrow afternoon. And Dan, did you have any parting comments before we close out?
No, but I'll tell you what, this is like the radio show. You'd get on and you do a national radio show for 2 hours every weekend, and it feels more like 10 minutes every